then the electric field strength, which is this one is positive, so here I will have positive charges, and this is negative, so here I will have negative charges. And we know that the electric field move from positive toward negative. So if you want to find this electric field, then you will use that formula, and your electric field will be equal to V divided by D. D is the distance between these two plates, and V is the electric potential. If that is 5 volts, so you will put 5 volts, and if this distance is 2 centimeters, so you will 5 divided by 2. That is centimeter, so you need to convert into meter. So in meter, that will be 0.02. In 1 centimeter, we have, no, in 1 meter, we have 100 centimeters. Okay, so, okay, electric field in parallel plates, okay, electric field in parallel plates will be uniform, okay. Uniform means the electric field strength at this point will be same as the electric field strength at this point. It will remain uniform. But in this case, the electric field will not be uniform field, okay. So here we are placing positive charges, and the electric field will be uniform at the middle, okay, over here, because at this point there will be some sort of fringing field. You can say that that is the fringing field. The field will be like this. Which one? You got this is equal to V divided by D. Or
yes.
Okay, you got this. Okay. Okay, so if we have a parallel plates, okay, like this. If you have a parallel plates, okay, and you connect the potential difference across these plates, and the potential is V, okay. Okay, you know what is mean by voltage and current. Why what is the difference between voltage and current? Voltage is just the energy, okay. Actually, in our circuit, let's say
What? Yes.
Okay, actually, let's say this is bulb, okay, and here I apply the potential difference across this bulb. So here I have voltage and current will flow like this. Oh, no, sorry, like this. That is the conventional current. So the potential is actually your energy, okay. It give energy to electron, okay. Electron got energy from this terminal, from positive terminal, and will move in this direction. So when electrons start motion, then that is the current, okay. So electron will come over here and will go over here and will come and will reach at this point. So here electron will deliver energy. So electron will deliver that energy which electron got from this terminal. After delivering energy to this bulb, electron will go again toward this terminal, okay. So and that energy is converted into light over here, okay. We got light from this bulb. So your voltage is actually the energy, okay. And here we have two simple plates, okay. These are the simple plates, and one plate is connected to negative terminal, and another plate is connected to positive terminal. So this is plus minus. So here I will got positive charges, and here I will got negative charges. And we know that electric field move from positive toward negative. So electric field will be like this, okay. And in parallel plates, the electric field will be uniform. Okay, uniform means the electric field strength at this point will remain same will remain same. At this point, electric field will be equal to electric field at this point. Okay, electric field will be equal to electric field at this point. This electric field will be equal to electric field at this point. So at all points, okay, electric field strength will be uniform. But electric field strength will be uniform in the middle, okay. At the corner, we have fringing field, okay. Electric field will be like this, and over here electric field will be like this. And these different types of electric field is known as fringing field. Okay, so let's say, and D is the distance between these two plates, okay. So let's say voltage is 5 volt, and this distance between these two plates is 2 centimeter. So that will be 5 divided by 0.02. 2 centimeter is equal to 0.02 meter. So SI unit. So your electric field strength will be equal to 5 divided by 0.02 meter. Okay, so now let's come toward the Coulomb law. Okay, so in 1785, a physician named Coulomb tell us that if you have two charges, okay, if you have two charges and that two charges are near to each other, then there will be some sort of force. That force will be either attractive force or that force will be either repulsive force. And if you want to find quantitatively that force, then that force will be directly proportional to the product of these two charges. Let's say this is my charge Q1, this is my charge Q2. Then the forces, attractive forces or repulsive forces, will be directly proportional to the product of two charges, and it will be inversely proportional to the square of the distance between them. It means that R is the distance between these two charges. And from the midpoint, okay, you will take the distance from the midpoint, and this will be your
Yes.
R. Okay, so it means that if you increase this R 2 times, okay, then your force will decrease 4 times, because we have inverse relation, and that is this, we have inverse square relation. Okay, mostly students do mistake over here, like force is inverse proportional to Q1 Q2 divided by R, but that is not R, that is R square. Okay, if we have different charges, then the force will be repulsive, and your this, that's the value of this will be negative. But if you have same charges like this, here we have positive positive or negative negative, then the force will be repulsive, because here we have same charges, and that repulsive force is represented by positive sign, or you will get force value that will be positive. And negative in opposite charges. Okay, so as force is direct proportion to Q1 Q2 divided by R, so force will be equal to K Q1 Q2 divided by R square, where K is the constant of proportionality. And your K value is equal to 1 divided by 4 pi epsilon naught. Epsilon naught in case of vacuum, but if you are using some sort of medium, like you place your charges in water, okay?
So 4 pi what?
Epsilon naught. Wait, I will write it below. Epsilon naught. Yeah, epsilon, okay? And this epsilon is equal to epsilon r, which is the relative permittivity, and epsilon naught. Permittivity of free space. Actually, if you have two charges, okay, and you place that two charges in water, okay, let's say this is water. Then tell me that this force will be higher, or if I place two charges in air, then this force will be higher, which is F2.
Sir, F2.
Why? So there is some sort of differentiation, okay? The distance between the two charges is same, and these two charges, the distance between these two charges is same as the distance between these two charges. And the charge value is also same, okay? This is also 1 coulomb, this will be 1 coulomb. 1 coulomb and 1 coulomb. So there is some sort of difference, and this difference is because of the medium. Here I am using water, okay, but here I am using air, okay. So this value bring that differentiation, epsilon permittivity, okay, and permittivity is equal to relative permittivity of this, and permittivity in vacuum. E naught have a constant value, and that is your epsilon naught, that has a constant value, and that is 8.85 times 10 to the power minus 12 force per meter. So, and it will always have a constant value, okay? So permittivity in vacuum is this. So if you want to apply the Coulomb law over here, so you will use this formula, okay? that will be F k Q1 Q2 divided by R square. K will be equal to 1 divided by 4 pi epsilon. Okay. And relative permittivity will be given to you. Okay. If the question is like this, find the force between two charges placed in water, and the relative permittivity of water is this. So then you will use this. But if the question is like this, that find the force between two charges, and that charges are present in vacuum, are located in vacuum, then in vacuum you will use 1 by 4 pi epsilon naught, because relative permittivity of vacuum is 1, and the other relative permittivity will be greater than 1. Okay. Actually,
so what is the value of epsilon?
so your epsilon value will be equal to relative permittivity, which is given to you. If in question water is included,
Yes.
then that will be given to you, and times this. Okay. So you need to remember this 8.85 times 10 to the power minus 12. But in vacuum, this is equal to E naught, epsilon naught, because relative permittivity of vacuum is equal to 1. Actually, relative permittivity give us a relation between permittivity in vacuum and the permittivity in any medium. That how much how much decrease in force will this medium will bring as compared to the decrease of the force in vacuum. You can say like this. Okay. So relative permittivity just give us the relation between permittivity of medium, any medium, and permittivity of the vacuum. Okay, so if the for vacuum you will use this formula. Okay, k is equal to 1 divided by 4 pi epsilon naught, and this epsilon naught is this value. So if you put that value over here, 4 times 3.1, 4 times this one, then that will be equal to 9 times 10 to the power 9. So if question is like this, find the force between two charges. Okay, and the charges is placed in vacuum, then you will use this value for k, instead of going to this whole multiplication like 4 pi and this value. Your k value will be equal to 9 times 10 to the power 9. Simple. But if some other medium is given to you, then you need to go toward this. You will do like 1 divided by 4 pi epsilon, and you need to find the epsilon value, which is equal to epsilon or epsilon naught. But if vacuum is given in question, then use this value, 9 times 10 to the power 9. That is simple, and you can easily remember this value, 9.9 or 9 times 10 to the power 9 force per meter. Okay, so the Coulomb law give me the force. Okay, and my force formula for my force is Q1 Q2 divided by 4 pi epsilon. I am using epsilon. Okay, R square. You also use this epsilon. Okay, actually, if vacuum is given to you, then this will become epsilon naught, and if any other medium is given to you, then this will be equal to epsilon naught times epsilon R. Okay, so now this formula, I will remember this formula only, and this force will be positive if I am using same charges, because if you multiply plus times plus, that is equal to positive, minus times minus is equal to positive. But if you use different charges, then minus times plus is equal to minus, and plus times minus is equal to minus. So you can say that if I got positive value, positive force, then the charges will be repulsive charges. But if I got minus value, negative value, okay, in answer, if you get negative value, then it means that the force is attractive. Okay, so electric field strength is equal to force per unit charge. Okay, I already discussed that I have this bigger charge, okay, and I am using test charge. So now I am going to apply the, let's say this charge is Q and this charge is small q. So electric field on this charge is force applied on this charge per coulomb, okay, this Q, and this is capital Q. Okay, so the force, if I apply Coulomb law on this, so that will be equal to F is equal to K Q small q divided by R square. This distance is R. Now, as we know that the electric field is equal to F divided by Q, so putting F value in this equation, so you will get K capital Q divided by R square into Q. So this Q will cut out by this Q, so you will get K Q divided by R square, or you can say that Q divided by 4 pi epsilon R square. Okay, so your electric field will be equal to Q divided by 4 pi epsilon R square. So it means that if only this charge is given to you, okay, if you have only this charge, and you want to find the electric field strength at this point. So now you don't use this test charge, okay? You don't use this test charge and find the force which acting on this test charge and use the value of this Q for this test charge. You only measure the distance, okay? You only measure the distance and apply this formula. So this charge you will put the value of this charge over here, 4 pi epsilon R square. So putting that value in this equation. So you will get electric field at this point. If you want to find electric field at this point, then you just need to measure this R. But if you want to measure electric field at some infinite point, practically infinite means at very, very, very far away from this charge. Okay, then it means my R is equal to infinity. So if you put R is equal to infinity in this equation, then your E will be equal to infinity. Zavera,
Sir, infinity.
your E will be equal to infinity.
Yes.
Okay. Okay, Zavera, in maths we study that the anything, let's say n is anything. Anything means if this is 2, 3, any integer value. If I divide this value by 0, okay, so anything divided by 0 will give you infinity.
Yes.
And if you divide it by infinity, then that will be equal to 0. Okay, so anything divided by, so this is, let's say, anything divided by infinity square is also equal to infinity, so that will be equal to 0. Okay, so if you want to measure electric field electric field strength at this point, then the electric field strength will be equal to 0. Okay, at infinite point. Okay. Okay, now let's move toward the electric potential. Up till we studied up till we only studied about, what is mean by kinetic energy, what is mean
Yes.
by potential energy. So if charge is moving with some sort of velocity, okay, then this charge will have kinetic energy. But if this charge is in static position, then this charge will have potential energy. Because energy is divided into two categories. One is the electric kinetic energy, another one is the potential energy. It means that your energy, first of all, energy is conserved. Okay, it will convert from one form into another form. Okay, energy is conserved. Conserved means energy will always be equal. Okay, energy is divided into kinetic energy and potential. So it means energy is convertible. Convertible means energy either in energy will
Lost.
yeah, it will not lost. It will be either in the form of kinetic energy or will either in the form of potential energy. So if your velocity is equal to 0, like in this case, then the kinetic energy will be equal to 0 because kinetic energy depend on velocity. Okay, then it will have only one energy, and that is the potential energy. So you can say that now if charge start moving from this point and reach at this point and stop, then it means that this kinetic energy is converted into potential energy. Okay, so this is all about the kinetic energy and potential energy. Now let's discuss it electrically, that what is mean by electric potential. Okay, so when we have two charges, okay, and let's say here I have another charge that is negative. Okay, so these two charges will attract to each other. And these two charges will not take the help of the external, okay, they will not require any external force to push it toward the negative charge. And similarly, this charge will also not require the external force which push it toward the positive charge. Okay, they will come toward each other because the charges are, because we are using different charges and different charge attract each other. So in this case, work done is equal to 0. Okay, because I am not applying any force on these two charges. But if I am using same charges over here, then as we know that same charges repel each other. Okay, so it will try to move in this direction, and it will also try to move in this direction. Okay, and if you apply the external force on this charge to bring it toward this direction, and here also if you apply external force, like you are pushing this charge toward the another same charge, okay, then you are doing work done. Okay, you are losing your own energy to bring these two charges together. Okay, so you are doing some sort of energy, and we know that energy is conserved. It will convert from one form to another, so it means that I am doing work done. So it means my work, which is also energy, is converted into a potential energy. Okay, it will move in this direction, and it will also move in this direction, and let's say it stop at this point. Then at this point, total energy will be potential energy. There will be no kinetic energy. But when you move from this position toward this, then there will be some sort of kinetic energy, but that kinetic energy will be less. So put at this point, my total energy will be potential energy. So this charge will store that potential energy in itself. Okay. So now, if the external force, if this force becomes zero, then these two charges will push back. Okay, will move in this direction and lose all of its potential energy. Okay, it will lose all of its potential energy and will move in this direction. Okay, and will come over here and become static. So this is your potential energy. Okay, if you bring it more closer, then more work you will do on these two same charges, then more potential energy will be stored in these two charges. Okay, let's say I have let's say, okay, energy changes. This is another topic. Energy changes. You understand that what is energy in electric field. So now energy changes in a uniform field. So first of all, we need to create a uniform field, and I already discussed that how you will create a uniform field. You just need to take two plates, okay, like this, and place it at distance d. So over here you will get the supply voltage. This will be V, this will be minus, this will be plus. Here I will get positive charges. Here I will get negative charges. Okay, so electric field will be from this toward this. Okay, so on all points, okay, all points, any points over here, equal force will apply on charge. Okay, if you take any point, equal force will apply on it as on charge. Actually, this is a uniform field, so there's an equal force will apply. Your electric field will be uniform. Okay, so if electric field is uniform, that means equal force will apply on any point. Okay. Okay. Now I want to measure the potential energy. So I will use test charge for this, okay? And okay, so and this test charge is, let's say, Q. So the if I place this charge at this point, then there will be no potential or no potential energy. Okay, there will be no potential energy. Okay, but when you bring it toward this, because I am not doing any work done over here. Okay, positive I place positive charge at this point, so positive charge is attracted toward this negative plate. So I am not doing any sort of work done. Okay, so potential energy will be equal to 0 at point A. Now let's say I am pushing this positive charge toward the positive plates. Okay, so I am doing work done on this positive charge, and it will come over here. So here potential energy will store in this positive charge. Okay, and that potential energy, that potential energy, let's say I am represented that by W, that will be equal to electric potential this and charge, multiplication of electric potential and charge. Okay, so here you will get zero potential energy, and here you will get maximum potential energy. Okay, when you place charge over here, bring charge over here, so you will do maximum work done and you will get maximum potential energy. Okay, so and you measure that potential energy over here. Okay, so if the or Earth is also have a zero potential energy. Okay, if anything placed on Earth, okay, let's say brick is placed on Earth, so this brick will have zero potential energy. But if you bring it upward, it means you are doing work on this brick. Okay, let's say at this point, so potential energy will store in this brick. Okay, and that potential energy, magnitude of that potential energy is m, mass of this brick, gravitational force g, which is 9.8, and h is the height, this height. Okay, in this case height is equal to 0, so your mgh, that will be you can find the potential energy using this formula. So similarly over here your potential energy is 0, but when you push this charge toward the positive plates, then you are doing work done and you are losing energy, and this charge is storing that energy in the form of potential energy, and you can find that potential energy by using this formula, V is equal to Q, V by Q. And your if you rearrange this equation, W is equal to QV, then that will be equal to V will be equal to W by Q. Okay. Okay, we also studied that the potential V is equal to, we also studied that V is equal to E B. Like electric field is equal to electric potential divided by distance between the plates. Okay, it means this electric field will be equal to potential times potential divided by distance between these two. Okay, these two plates. Mostly students confused in this equation. Most students said that E is equal to VD, but that is wrong. Okay, your V is equal to ED. Remember it like this. V is equal to ED. Okay, so when you so my in this charges, okay, let's say one charge is this one, and another other charges are these. These are the other charges. Okay, so if you bring it toward this, then the electric potential will increase because I am decreasing d value. Okay, I am decreasing d value between these two charges. So if you decrease d value, then electric field between these two plates will get increased. E will be equal to V divided by D. So if you get decrease, then E will increase and your voltage will also increase. And if you draw the graph, okay, if you draw the graph, then the graph will be like this. This is D. Here I have positive charges that move in this direction. Here I have potential energy. So, so when I bring this charge toward this terminal, then the potential energy will get increased. Okay, and potential energy will increase linearly. So your graph will be like this. Your potential energy will increase with distance. If you move along the distance, your potential energy will increase like this. Okay. So here you will get maximum potential energy, and here you will get zero potential energy, okay, or minimum potential energy. So here you will get zero, and this will be your maximum potential energy. Okay, so we also studied that E is equal to Q divided by 4 pi epsilon R square. This will be R square in terms of E. Okay, before going to this equation, okay, there is one point left in this lecture. There is a term that is the equipotential. Equipotential means equal potential. So let's say I am using another charge, okay, and that I place that charge over here. So when I bring, I will do work done on this charge like as I did on work done on this charge, and I will bring it toward here. Then the potential energy, this is let's say potential energy P2, which is stored in this charge, and let's say this potential energy PE1. So PE1 will be equal to PE2 or PE1 will not be equal to PE2. Whether this will be equal to PE2 or it will not be equal to PE2.
So which one?
Now I am using two charges, okay? One is this charge and another is this charge. I bring this charge over here, okay, and place this at this point. Then after this, I pick up another charge and bring that charge over here. So now there is some sort of potential energy. Potential energy at this point is equal to 0, but now at this point there is some sort of potential energy, and at this point there is also some
So
sort of
in both points it will be same.
yes, and in both points, potential energy E1 will be equal to potential energy E2. Okay, if I do more work on this charge and bring that charge over here, and also bring this charge over here, then still the potential energy of this charge will be equal to the potential energy of this charge. Okay, so you can say that these are the equipotential lines. Okay, on these lines, if you place your charges, then the potential energy of this charge will be equal to the potential energy of this charge, and that should be equal to potential energy of this charge. So you can say that these are my equipotential lines. Okay, so these are the equipotential lines. Zubaira, in positive charge, let's say I have a spherical positive charge. Okay, the electric field will be like this. So can you draw the equipotential line? This will be the equipotential line. Or this will be the equipotential line.
Sir, I think the circle one.
Yeah, the circle one will be your equipotential circle. Yeah, you can say equipotential circle. Okay. Mostly MCQs come like this, that if you have a sphere, okay, and inside sphere we have 10 Coulomb charge. Okay, inside sphere we have 10 Coulomb charge, and on this surface, this sphere, I am putting another layer, or yeah, another layer. Okay, so what will be the charges? What will be the value of charges on this surface? Okay, so your answer should be equal to, that charges will be equal to 10 Coulomb. Okay, as the lines are moving outward. Okay, this is, let's say, positive charge, positive 10. So the lines will be like this.
Yes.
Okay, so here you will get 10 Coulomb like this. Here you will get 10 Coulomb, 10 Coulomb, 10 Coulomb, 10 Coulomb, 10 Coulomb. So here you will also get 10 Coulomb, 10 Coulomb, 10 Coulomb on this surface. Okay, so most MCQs come like the charges will be 10 Coulomb, or the charges will be 0 Coulomb, or the charges will be minus 10 Coulomb. Where if I place another charge, if I place another charge like this, and that is minus 10 Coulomb, then what will be the charge on this surface? That will be equal to plus 10, 0 Coulomb, minus 10 Coulomb. What do you think that what will be the potential on the surface, external surface?
Sir, 0.
Yes, the potential will be 0, okay? Because all these fields will move and will attract you toward this, like this. Okay, if you have charge that is 10 Coulomb, this is plus 1. And let's also this is plus 1, okay? Same charges. Then the electric field will be like this. What will be the potential at point A?
Sir, it will still be 0.
Yeah, that will be equal to 0, okay? The electric field at this point will be equal to 0. Okay, so here I told you that the potential energy will be equal to 0, but here the potential energy will be maximum. So let's say you have 3 resistance, okay? And here I am going to supply, that is 10 volt. It means here I plus 10 volt, and here I will get 0 volt. What will be the voltage at point A, and what will be the voltage at point B? Let's say this resistance is 4 ohm, this resistance is 12 ohm, and this resistance is also 4 ohm. So what will be the potential at A, B, C, and D?
Sir, at A will be 10.
Yeah, at A it will be 10. Good.
So will it decrease?
Yeah, it will get decreased, okay, and here the potential will be equal to 0. So
B.
yeah, at B will be equal to 0 volt. Uh, that is same like this, okay. Here I will get 0 volt like this. This is B point, and here I will get maximum, that is 10 volt, okay. And this potential will decrease on way, and it will become 0 over here, okay. So potential at this point you can find it by, like, you need to find current first of all. So your current will be equal to, as we know, I is equal to V by R. You need to apply the Ohm law. Voltage is 10 volt. R is, so this plus these are in series. So R is 20. In this case, R is 20. So your current will be equal to 5.5 ampere. Now you need to find that how much potential drop will occur in this resistor. Electron will get energy from this terminal and will move over here and will not lose any energy. Okay, so that's why the potential voltage at this point will be equal to 10 volt, because in electron, not energy at any component on way. Okay, there is no component, so no energy will lose. But here we have a resistor, so electron will release some energy, then it will release some other energy which left with electron, then it will release all of the energy over here, and it will become 0 volt over here. Okay, so let's find how much energy it will lose in 4 ohm resistor. So as we need to find this potential, that how much voltage, how much energy this resistor will consume. So as we know, that V is equal to IR. So R is 4, I is half, 1 by 2. So your voltage drop in this resistor will be equal to 2 volt. So it means out of 10 volt, this resistor will get 2 volt and leave the other. So here I will get 8 volt. You can say the potential at this point is 8 volt. Now let's find this. So that should be current is 1 by 2. Resistor in this case is 12. So that should be equal to 6 volt. Now this resistor will consume 6 volt out of 8. So here you will get 2 volt. For this, that's 1 by 2 times 4, that's equal to 2 volt. So this will consume all the voltage, and here you will get 0 volt. So your potential energy is decreasing if you move down, okay? And that is converted into heat, okay? So this electrical energy will convert into heat, okay? Here also the energy is converted into a heat. Okay. We studied that the E is equal to Q divided by 4 pi epsilon r square. And we also studied that the E is equal to V divided by D. So E is equal to Q divided by 4 pi epsilon r square. So in terms of R, let's say this is also equal to R. Okay, D or R, you can use R or E. So this E is equal to Q divided by 4 pi epsilon. So Q divided by 4 pi epsilon r square will be equal to V divided by R. So this R will cut out by this square. So your V will be equal to Q divided by 4 pi epsilon R. So it
So
means,
why will it be? So I did not understand. B by R.
okay, V by R. Actually, R is not the radius, okay? You must remember this, that R is not the radius. R is the distance between these two charges. You can use D over here, but you will put D square over here then. Okay, got it?
Yes, sir.
Okay, so here I use D. D is simple distance, okay? So you can use R over here. Okay, so your V by R, yeah, V by D. So 2 divided by 4 pi. So this will be, so your potential is inversely proportional to the distance between two plates, okay? Distance between two plates, not the square of the distance between two plates, okay? So you should be careful in writing the formula for V and E. In E there will be square, in V there will not be any sort of square over here, okay? And also electric, this is a scalar quantity. Mostly in MCQs, such MCQs come that electric potential is a scalar quantity or vector, so it is a scalar quantity. but electric potential is a vector quantity. It depends on direction, okay, and it doesn't depend on the direction. Also, potential is energy, so that's why it is energy also scalar quantity. So that's why. Okay, if you want to draw the graph, okay, then the graph will be like this. This is distance d, d or r. This is voltage. Let's say this is positive volt. So when you move away from this charge, okay, when you move away, then the voltage will get decreased. If you bring the test charge in this direction, then the potential difference between these two charges will get decreased because I am increasing R. If you increase R, then the potential difference will get increased. Voltage between these two charges will get decreased. And that decrease will be like this. This is the potential. So that will decrease like this. Their potential will decrease like this, okay? Along with distance, it will decrease like this. If you move in this direction, it will decrease like this. If you move in this direction, then it will decrease like this. So as you see, if you move in this direction, then same potential decrease come as like if you move in this direction. So you can say that this potential does not depend on the direction. As you see, same decrease come in both directions. So it does not depend on the direction.
So will the chapter finish today?
Okay, so give me just few minutes. Okay. Okay, there is only one topic which I want to discuss. Then this chapter, we will finish this chapter. Got it? Okay, this is positive charge, okay? And let's say this is infinity. So energy at infinity will be equal to 0. It means that if you place positive test charge over here, then there will be no any potential energy stored in this positive test charge. But when you move toward this bigger charge, then potential energy will be stored in this charge, and that potential energy will be positive potential energy. Okay, if it come over here, but if you bring it backward, then the potential energy will be minus, because potential energy decrease if you move it from here to here, and if you move it from here to here, then the potential energy will be positive. It means potential energy will get increased in this direction. So if you want to define the potential energy, then you can write it like potential energy at a point is equal to work done in bringing unit positive charge from infinity to that point. This point, electric potential at point is equal to work done in bringing unit positive charge from infinity to that point. Okay. Okay. So there is only one topic, that is the difference between electric field and gravitational field. So tomorrow we will discuss that. Okay.
Okay, sir.
Yeah. Then we will start another chapter that is known as the capacitor. Okay.
So tomorrow we have to discuss the past paper.
Okay, so we will do the past paper. If you have any past paper, or if you search past paper on internet, then it will be good. I will solve that question.
Okay, sir.
Okay, you just actually there are different type of past paper. So you search their past paper and send me. I will we will discuss that past paper in tomorrow class. Okay.
Okay, sir.
Then after this there is a capacitor chapter. So you need to search this chapter. Okay, past paper you need to search this chapter. Actually, there is one.
No, sir, I'm talking about communication.
Okay, that past paper. Okay, got it. Okay, we will discuss that past paper tomorrow, and we will also. That is not too much. We will also start the new chapter. Okay.
Yes, sir.
Capacitor. Okay.